Okay, for this video, I'll be going through DC circuit tutorial 2. Okay, figure 1.1 shows a DC circuit. On figure 1.1, indicate the direction of the conventional current. So the longer side of the battery is actually positive and current comes out from the positive terminal. Okay, the shorter side is the negative terminal and electrons actually comes out from the negative terminal. Okay, and back to the positive terminal. Okay, when switch S is open, okay, calculate the effective resistance of the three resistors. So basically, they are, if current were to flow, right, you'll find that they are actually connected in series. So you can just add them up. It's 18 ohm. Then part 2, calculate the current drawn from the battery. So if I were to withdraw the effective resistance as 18 ohms, okay, I keep this 12 volts. Then this is my V, this is my R. I can actually find my I. So V equals to IR, I get 0.67 ampere. Now the current flowing through R3. So because they are now all connected in series, so the current will be the same throughout in a series connection. Now the potential difference across R2. So R2 is over here. Okay, R2 is having a resistance of 6 ohm. Okay, and we know that the current flowing through it is 0.67 ampere. So using V equals to IR, 0.67 multiplied by 6, we will get a value of 4 volts. Okay, or you can actually use your potential divider formula. Potential divider formula, which is using its own resistance over the sum of resistance. So take note, the potential divider formula only works for series connection. Okay. Now when switch S is closed, calculate the current drawn from the battery. So it is good to always withdraw. Okay, before I go down to withdraw, when switch S is closed, okay, the top path, this path actually has no resistance, okay, in the wire. So basically this is a short circuit, meaning all the current that comes to this node here will pass through this path of no resistance or pass through the short circuit, thereby bypassing the 8 ohm resistor. That means I can redraw the circuit as 4 ohm, 6 ohm, and 12 volts. Okay, so I can continue to simplify this circuit because they are now connected in series. I can add them up, and in so I can then calculate the current, which is 12 divided by 4.6, which is 10 ohm. I'll get 1.2 ampere. So they want us to calculate the potential difference across R2 now. So R2 is actually our 6 ohm resistor. Okay, so if we go back to this original circuit, okay, we know that the current flowing through is 1.2 ampere. We want to find the voltage or potential difference across this 6 ohm. We take V equals to IR. I is 1.2, R is 6, so we get 7.2. Okay, just for practice, can we calculate the potential difference across the 4 ohm? We call it V1. Okay, we know that the current is the same, 1.2 ampere, so equals to I multiplied by R equals to 1.2 times R of 4 ohm, we get 4.8 volts. Now if we add them up, we sum them up, it will be equal to 12 volts, which is actually the EMF that is being supplied to the circuit. Okay, so in series, the potential difference is sum. The current is the same. Okay, figure 2.1 shows a DC circuit. What's the effective resistance between X and Y? So between X and Y, we see that there are R1 and R2 connected in series, and R3 is connected in parallel to the series of R1 and R2. So we can actually simplify R1 and R2 to be 12 ohm, and if I were to redraw, I will have 12 ohm here. So if this is my X and this is my Y, I would have R3 6 ohm connected in parallel. So I use the parallel resistor formula. I should be able to get 4 ohms. Okay, so please remember to flip, because once I get 1 over R equals to 1 over 4, that is not the final answer. I need to flip so that I get R equals to 4 ohms. Now they want us to calculate the current flowing through R4. Okay, so we can actually redraw the whole circuit. We know that for this part, they want us to calculate the effective resistance, right? And this gives us a value of 4 ohm. And this 8 ohm is my R4, which I haven't touched yet. 24 volts here. So actually I can simplify this further to get 12 ohm because they are connected in series. Now they want us to find the current that flows through R4, which is effectively the current that flows through 4 ohm as well, because in series the current is the same. So we apply V equals to IR. So I equals to V over R equals to 24 over 12 equals to 2 ampere. Okay, so the current that comes out from the battery is 2 ampere. So if I were to fit this back to this first circuit, or this circuit that we have redrawn, we know that the current in series is the same. So the current that flows through the 8 ohm will be 2 ampere. Now they want us to find the potential difference across R4, which is this. So 2 ampere is the current that flows through. We have the resistance as 8 ohm. So using V equals to IR, the I is 2, R is 8, so we get 16 volts. Okay, so again, we'll like to check if our answers is okay, is valid or not. We can also find the V for this across this 4 ohm. So using V equals IR, we already know that the current flowing through will be the same in series. Multiplied by 4, we get 8 volts. Now, the two resistors are connected in series. Therefore, if we were to sum up their potential difference, we should get the same 24 volts as the EMF. So this is a way to check in your exam. Okay, now they want us to calculate the potential difference between X and Y. So where did we get this 4 ohm? This 4 ohm is actually from the parallel connection of this, right? The 12 ohm and the 6 ohm, so that we can get our 4 ohms, right? So the potential difference across X and Y will then be equals to 8 volts. Okay. Now what's the current flowing through R2? Where's R2? Okay, maybe I clean this up a bit. Okay, but we had a lot of information from the redrawn circuit, so we'll put them in here. We know that the potential difference across XY is actually 8 volts, right? Across this is 16 volts, and they add up to become 24 volts. So R2 is over here. Okay, so because in parallel the potential difference is the same, therefore I know that over here will also have 8 volts. Okay, now if I were to just consider the top part of this parallel circuit, the effective resistance is actually 2 plus 10 equals to 12 ohm. Okay, and I know that the potential difference across this 12 ohm is 8 volts. Therefore, I can then find the current through the top part by using V equals IR. My V is 8, my I is unknown, my R is 12, sorry, because it's the sum of the two resistors in the top half. So my I will be 0.67. Okay, 0.67 ampere. Okay, so I would like to also do the bottom half, which is this. So I know that the potential difference is 8 and there's only one resistor. So V equals to IR. V equals to IR. My V is 8. My I is unknown, which I want to find. The resistance is 6. Therefore, I equals to 8 over 6 equals to 1.33 ampere. Okay. Now, if you know, the current in a parallel circuit is the sum. That means the current here is 0.67 ampere. Here is 1.33 ampere. And if you sum them up, it will actually be 0.67 plus 1.33 equals to 2 ampere. Now, did we get the current coming out from the battery to be 2 ampere? Yes. So this is another way that you can check in your exam that all your calculation makes sense. Okay. So now they want us to find the potential difference across R2. So this is R2. So since I have 0.67 passing through, the voltage will be 6.7. Okay, that means I will have 1.33 over here, the voltage. And if you add them up together, it will be equal to 8 volts. So if your calculations are all correct, your theories you apply correctly, you can actually check for all your answers during exam and test. Okay, so this is the voltage divider rule. So it works only for resistors that are connected in series. Okay. Okay, then we have this current divider rule. It can only work for two parallel paths. So actually, it's not that useful lah. Because if they were to present us with three resistors in parallel, then we can't really use this. So you can only just focus on the voltage divider rule or potential divider. Okay, question 3. We have a 16-volt battery. We have R1 3.2, R2 12 ohm, R3 is 8 ohm, and R4 is 8 ohm. Okay, so if you are more comfortable, you can actually redraw this very quickly to look something like this: 12 ohm, 8 ohms. Okay, then we can actually pull this down to here, 8 ohm. Okay, so that it looks more like the usual circuit that you are familiar with. Okay, so they want us to calculate the voltage drop across each resistor, which is to calculate the potential difference. Okay, so for R1, okay, maybe we can actually calculate the effective resistance of these two resistors in parallel. So it's 1 over 12 plus 1 over 8. Okay, so it is actually effective resistance of 4.8. Okay, I actually look at the answer here. Okay, I don't have my calculator. So actually I can redraw everything. Okay, because I never do anything to 3.2 ohms. I did something to the 12 ohm and the 8 ohms in parallel. My 8 ohms, the last 8 ohm, I didn't do anything. So I just put in my effective resistance of 4.8 ohm. And I redraw everything. So this circuit actually becomes simpler once you redraw it. Okay, so now we are ready to apply the potential divider formula. Okay, so for the 3.2 ohm, V 3.2 ohm will be equal to 3.2 over the total, the sum of the resistors in series. Okay, because the potential divider formula only works for resistors in series. So it's 3.2 plus 4.8 plus 8. Okay, multiplied by the EMF, which is 16. So 3.2 plus 4.8 is 8. 8 plus 8 is 16. So we get 3.2 volts. Okay. But what if we do not remember how to use the potential divider formula? Very simple. You can actually add up all the resistors in series. This you know. It becomes 16 ohm. Okay, and this is 16 volts. I can actually find the current, which is 1 ampere. So I put this current of 1 ampere back here. I can just use the current of 1 ampere to find the potential difference, which is 3.2. For this will be 8 volts because it is 1 ampere passing throughout the whole circuit, because in series the current is the same. So V equals to IR. The I is 1 ampere. The resistance is 8 ohms, so it will be 8 volts. Okay, and similarly this will be 4.8 volts. Okay, now to see whether your answer is correct, resistors in series, the potential difference is the sum, and it must be, the sum must be equals to the EMF. So 3.2 plus 4.8 plus 8 is equals to 16 volt. So that means our calculation is valid. Okay, so you can do this either by using the potential divider formula, or you can find the current. Okay, so when I mark, most of you were able to get this. Now calculate the current through each resistor. Okay, for these two, the 3.2 and 8 ohm, the last 8 ohm, the current is actually 1 ampere. But because this 4.8 ohm resistor, was from the two resistors in parallel. Okay, so it's a little bit complicated. But because we know that the potential difference across here is 4.8 volts, where did we get this from? It's from here, right? So if I were to treat this as a whole bracket, okay, the resistance is actually 4.8 ohm. But this 4.8 ohm is actually formed by these two resistors in parallel. And because the potential difference across these 4.8 ohms is 4.8 volts, therefore across here must also be 4.8 volts. Alright, and in parallel connection, the potential difference will be the same. So since these two are connected in parallel, they will both have the potential difference of 4.8 volts. So how do we find the current? For R2, it will just be the potential difference divided by resistance of 12. How do we find the current through R3? It will be 4.8 volts divided by the resistance of 8 ohm. And the current that, so this is IR2, that means it is the current that flows through the R2 resistor. And IR3 is 0.6. You notice that when I sum them up, it is equal to the main current. So again, during exam and test, you can actually test your answers. You can actually verify your answer. Okay, question 4, it shows a circuit. The battery and ammeter have negligible internal resistance, so we don't need to care about their resistance. When switch S is open, voltmeter reads 4.2. Now, switch S is open, I'm just going to redraw the circuit. So if switch S is open, I'm going to ignore the 8 ohm here. So this is 12 ohm. And I still have my voltmeter here. Okay. And this is connected in series to the R. So this is what happens when the switch is open. By spending 1 minute or less to redraw the circuit, you make it clearer. So this 12 ohm and R, they are connected in series. Now they tell us now that this voltmeter reads 4.2 volts. Okay, and since they are connected in series, I'm going to say that the potential difference across here is 1.8 volts. Right? Why? Because this is 4.2 volts, this is 1.8 volts. The two resistors are connected in series. In series, the potential difference is the sum across each resistor. So if this is 4.2, I can take 6 minus 4.2, I will get 1.8 volts. Okay? But they are asking us to calculate the current reading on the ammeter. Okay? So a lot of students, they will actually use 6 volts divided by 12, which is not true, because that is not the potential difference across the 12 ohm. The 4.2 volts is the real potential difference across the 12 ohm. Okay, 4.2 volts. So I should use 4.2 divided by 12, I get 0.35. And if it's 0.35, that means I will have this current of 0.35 ampere flowing into R as well. So I can actually calculate the resistance by using V equals to IR. The potential difference is 1.8. So 1.8 equals to 0.35 multiplied by R, which is unknown. So R will be 1.8 over 0.35, and the answer will be 5.1 ohm. Okay, the switch S is now closed. So if it's closed, I can just redraw the circuit just to make it clearer. 8 ohm and 12 ohm. So now they are in parallel, and then it's connected to my resistance of 5.1 ohm, which I found from there. Okay, so the voltage or the EMF of a battery is 6 volt. So they are asking for what's the new reading on the ammeter and voltmeter. So voltmeter is across here, ammeter is across here, is through here, right? So I would actually need to find the effective resistance of this. Okay, so the effective resistance will then be 1 over 8 plus 1 over 12 by using the parallel resistors formula. So 1 over IFF equals to okay, so the effective resistance, okay, if I remember to flip, it will be 4.8 ohm. Okay, so I can actually redraw the circuit again. Okay, that means I show 4.8 ohm here, And then because I never do anything to the 5.1 ohm, I just draw it as it is. So actually when you redraw, so I stress this again, it makes the circuit looks simpler. And my ammeter is here. My voltmeter is actually across this 4.8 volts, 4.8 ohm resistor. Yeah, because look at this pink color box that I put around this parallel resistor, right? So I'm able to get 4.8 ohm by using the parallel resistors formula, and my V is just across this pink color box. So my V is also across this pink color effective resistance, right? So now that we have this, we can either apply a potential divider formula, or we can simplify this circuit even more, because I can then get a effective resistance of 9.9 ohm, right? Because now they are connected in series. So 6 volt divided by 9.9, it will be the current will be 0.606 ampere. Okay, so that will be the reading of the ammeter. Because it's connected directly after the battery, it will measure the current in the main branch, which is 0.606. So if I have current of 0.606, I bring it back to this circuit that we have drawn. Okay, I'll just erase my ammeter, because you know that the current now is 0.606 ampere. So for current, usually I'll draw it on the branch itself, but for voltage, I will draw across. Okay, so now I need to find the potential difference across this 4.8 ohm, or the voltmeter reading. And because the current is 0.606, the resistance is 4.8, I can then use my V equals IR. 0.606 multiplied by 4.8, I will get an answer of 2.91 V. Okay, and just to check that our answers make sense, okay, I'm now going to find the potential difference across this 5.1 ohm, right? So I know the current is going to be 0.606 passing through the 5.1 ohm, because it is the same current in a series connection, right? So 0.606 multiplied by 5.1, I get 3.906 volts. Okay, just to 3.0906. Okay, so I can actually add the 3.0906 to 2.91. It should be equal to 6 volts. So that is how I can verify the answers. Okay, so besides working out the answers, you must also try to verify to see if your answers make sense or not.